Let us start by recalling a few things that we did in the last lecture. Prima facie, it appears that almost all sets that we come across are measurable. Practically, most of the subsets of R which we deal with are measurable. That's what it appears. So, natural question is whether there exists, if at all, some non-measurable sets. And towards it, with some involved work by using axiom of choice, etc., we established existence of non-measurable sets. That is one thing that we did in the last lecture. So, non-measurable sets, though may be rare, definitely exist. Now the question is it really rare? And towards that, we found that no, you can have as many non-measurable sets as there are measurable sets. To make all these things precise, we used cardinality idea. So let me just quickly remind you all those things before going to the next topic. M is the collection of all Lebesgue measurable sets. As I remarked already, prima facie, it appears that almost all sets that we deal in practice are measurable. However, we have seen that cardinality of measurable sets, collection of all measurable sets, is same as cardinality of 2 power r, which by standard notation is 2 power c, where c is cardinality of continuum. And then we saw there exists non-measurable sets. For that, we invoked axiom of choice. Once existence of non-measurable sets is clear, using that, we could establish that cardinality of collection of all non-measurable sets is also 2 power c. So in that sense, there are as many non-measurable sets as there are measurable sets. or both are same as number of subsets of R. So as you can see, a structure of measurable set may be very complicated. As I told you several times, almost all sets that you deal in practice are measurable. The measurable sets can be very complicated. What next we observe is that these complicated measurable sets can be approximated by nice measurable sets. For instance, open sets. For instance, closed sets. For instance, F sigma sets. For instance, G delta sets, and so on. These are nice measurable sets whose structure seems to be more convenient to deal with than an arbitrary measurable set. So our next aim is to see that an arbitrary measurable set can be approximated with the help of nice measurable sets. Okay. That's the intuitive understanding of what we are going to do. Let us make it precise. Okay. In fact, a few things in this direction we have already done either in lecture classes or in our tutorial classes. So we shall repeat a few things and then state it more precisely. So far, so good. Is it clear what we are going to do next?
Yes, sir.
So can you just recall what we are going to do next? What I told, repeat so that everyone will be, it will be useful for all. Yeah. What we are going to do next is? Yeah, please, one of you can tell me.
So we are going to
Yes, go ahead. Go ahead. Yeah, we are going to somehow establish that an arbitrary measurable set can be approximated well with the nice measurable sets. What are all these nice measurable sets, etc.? And what do you mean by approximation? And those things we are going to see. And these type of theorem are generally called regularity theorems. Okay. With that introduction, let us go into the details. Okay. Recall that some preparatory facts we have already done. However, for the sake of exposition and completeness, let us repeat it. Recall that for E subset of R, M star of E, the Lebesgue outer measure of E, is defined as infimum of summation length of In. E is contained in union in In open interval. The infimum is taken over collection of all countable family of interval that covers E. Since M star E is infimum of a set, if you increase it by a bit, that cannot become a lower bound. So given epsilon greater than 0, M star E plus epsilon is not a lower bound. There exists a countable collection of open intervals In such that E is contained in union in and summation of length of in is less than or equal to m star of E plus epsilon. Simple application of definition of infimum. Okay. Now you take G to be union in. Since INs are open intervals, in particular they are open and countable union of open set is open, therefore G is open, which is open. So you could construct an open set. Further, since E is contained in union in, E is contained in G and E is contained in G. Now M star of G is equal to M star of union in. By countable subadditivity, this is less than or equal to summation n M star of in. And since INs are intervals, outer measure is length of in. And you took in such that summation n L of in is less than or equal to M star of E plus epsilon. So given a complicated set E, I have found an open set G enclosing E and outer measure of G is at the maximum outer measure of E plus epsilon. This epsilon at your disposal is at your control. This we have seen several times. Now, I don't know whether E is measurable or not. Let us assume that E is measurable and also that the outer measure, which is same as measure in case it is measurable, is finite. Suppose E is measurable and M of E, which is of course same as M star of E, is finite. Okay. Now G being open is measurable. Keep that in mind. Okay. Now you can write G, the bigger open set, as E union G minus E. And M of G is okay because G is measurable, is equal to M of E union G minus E. Since G is measurable, E is measurable, you will get G minus E is measurable. Yes or no?
Yes, sir.
How does it follow?
Sir, it is sigma algebra.
Sigma algebra.
Let me see. Yeah.
So this will be M of E plus M of G minus E. Will you agree?
Yes, sir.
Because countably additive, M is countably additive. Okay. And therefore, M of G minus E is M of G minus M of E. You can talk about minus M of E and so on because M of E is finite. So this makes sense. Okay. But what is M of E? G minus M of E is less than or equal to epsilon. So what did you get? You get that M of the difference G minus E is less than or equal to epsilon. Thus, in case the given set is measurable, then you can find a open set G enclosing it such that the measure of the annulus part, let me roughly call it as annulus, the annulus part, this part is less than epsilon. This is measure of the residual, measure of the difference is less than epsilon. And epsilon is at your disposal. Okay. Now, what we are going to observe is that the assumption that M star of E or M of E is finite can be avoided, and still we can get this result. Okay. Which result? The result that the measure of the remaining part is less than or equal to epsilon. I repeat, given a measurable set, you can always find an open set such that the measure of the difference is less than or equal to epsilon. We don't want the condition that measure of the given set is finite. If it is finite, everything is working fine. Even if it is infinite, same result holds. Okay. Now let me make it as a precise theorem, precise statement. Let E be a subset of R. Then the following are equivalent. The following are equivalent. If one of the following statement holds, then all other statements will turn out to be true. First statement is that E belongs to M. That is, E is measurable. 2. I am not assuming measure of E is finite. E is measurable. That's it. 4. Each epsilon greater than 0, there exists an open set. There exists an open set G such that E is contained in G. G encloses the given set, and measure of their difference, outer measure of their difference, G minus E, can be made less than or equal to epsilon. And third statement, there exists a G delta set what I will call, I can call V, a G delta set V such that the given measurable set E is contained in V, and measure of, outer measure of the difference V minus E is 0. There exist open sets for each epsilon. There exists an open set such that M star of the difference G minus E can be made less than or equal to epsilon, and there exists a G delta set such that E is contained in V, and measure of V minus E is equal to 0. There is no difference. As far as outer measure is concerned, there is no difference. Okay. These three statements are equivalent. Before entering into the proof, let me draw your attention to the fact that in the second statement and third statement, we are talking about M star, not M. Can I replace M star with M? Can you hear me?
Yes, sir.
I repeat the question. There are three statements and we are about to prove that these three statements are equivalent. My question is, in the second statement and third statement, can I replace this M star with M?
Yes, sir, because E is measurable.
That is slightly, you should be careful. It is actually if and only if. E is measurable implies this. There you can replace M star with M. But we want to prove the converse also. If that is true, then E is measurable. In that case, to take this is true, I don't know whether G minus C, V minus C, etc. are measurable or not. So I cannot use a priori M. Are you getting me?
Yes, sir.
So E is measurable with that assumption. If you proceed, then you can replace M star with M. But we want to talk about the converse also. While talking about the converse, I don't know whether E is measurable, but I have to prove E is measurable. Okay. So in that case, I cannot write M in place of M star. So this is the right way to express the theorem. Now, without further ado, let us go to the proof of the theorem. Proof. Some part of the theorem we have already proved. In fact, before writing the statement, I have told you that I can find an open set such that M of G minus E is less than or equal to epsilon if E is measurable and it is of finite measure. But now the theorem drops that assumption. Finite measure assumption is dropped. Still you can do it. That's what the theorem says. So definitely there will be some overlap with what we have done already. Again, for the completion of the proof, I should repeat those things. So first let me prove 1 implies 2. 1 implies 2. Okay. Assume E is measurable. I have to prove that given epsilon, there exists an open set and so on. As a first step, I will assume E is of finite measure. Okay. Let epsilon greater than 0. I have to find an open set, and for doing that, I will first assume E is of finite measure. Let us consider the case. Let us consider the case M of E or M star of E. Here you can talk M of E also because E is in M, is finite. Okay. Then, since we have already done, let me quickly repeat that. There exists a countable collection of open intervals In such that E is contained in union In and summation length of In is less than or equal to M star E plus epsilon using definition infimum. Okay. Now take G equal to union En. Then G is open, E is contained in G, and M star of G is equal to M star of union In. This is the repetition of what we have done before the theorem. This is less than or equal to summation n L of In, and it is less than or equal to M star of E plus epsilon. Okay. Now we want to talk about the annulus. Since G is in M, why? Because G is open. E is in M, why? That is our assumption. G minus E is in M, and outer measure of E plus outer measure of G minus E is equal to outer measure of G by countable additivity. This is less than or equal to outer measure of E plus epsilon. Now, since outer measure is finite, you can cancel from both sides. Therefore, M star of G minus E is less than or equal to epsilon. Okay. So things works when M star of E is less than infinity. Now let us consider the case. Now suppose M star of E is not necessarily finite. Then how do you tackle? You have to make it into a reduce to a problem where you have measurable set with a finite measure. For that, I consider En equal to E, whose measure I don't know whether finite or not, intersection minus N. If you don't know how to solve a problem, reduce it to a problem which you know how to solve. So you don't know how to handle the case when M star is of infinite measure, then you reduce it into the case where it is finite measure. Okay, so I define En to be like this for every n in n. Then do you agree that Ens are of finite measure?
Yes, sir.
How does it follow? First of all, whether Ens are measurable. Ens are measurable, intervals are measurable, therefore intersection is measurable, therefore En is measurable. And En is inside the interval minus n, and that interval minus n is of finite length for each fixed n. It is of finite length. Therefore, measure of Ens would be finite. Then M star of En. In fact, I can talk about M of En. M star of En is finite. Okay. You can see that E is equal to union En. Okay. Do you agree?
Yes, sir.
That is just a theory. Now, since Ens are measurable and Ens are of finite measure, let me write then En is measurable and M star of En is finite. That part you have already proved. If E is measurable and measure of E is less than infinity, then you can find an open set part you have already proved. Okay. So instead of applying it for E, apply it for En. By what we proved, can you complete that statement? By what we proved, what you can find? Is it that difficult?
An open set for each En.
For each En. So please make it with a notation. There exists open sets. I will call it as, let us say, Gn, such that En, which is measurable and finite measure, is contained in Gn, and M star of the difference, residual, annulus part, Gn minus En, is less than or equal to any number I want. I will make it as epsilon by 2 power n, which is some epsilon dash. We will now come to know why this 2 power n. Okay. Now take, I want to produce a G covering E. Now I got Gns covering Ens. Okay. Take G is equal to, any guess?
Union Gn.
Union Gn, yes. union Gn. Then G is open, first of all. G is open, being a countable union of open set. Then, since E is union En and Ens are contained in Gn, E will be contained in union Gn. And E, which is equal to union N En, is contained in union N Gn, which is equal to G. So E is contained in G. That is, E is contained in G. So you got an open set enclosing E. What more is needed is the difference has measure less than or equal to epsilon. So let us find M star of the difference G minus E is less than or equal to, do you agree with this? What is G minus E? First, let us try that and then find M star. G minus E I wanted to have, and then I want to find its outer measure. G minus E is union Gn minus union En. That is how we define G and E. Okay. And this is equal to union Gn minus En. You can verify this. Okay. N in N. And therefore, M star of G minus E is equal to M star of, even if this is contained in, I don't bother, union N in N, Gn minus En. Okay. And this is less than or equal to summation N M star of Gn minus En by countable subadditivity. Summation N M star of Gn minus En is less than or equal to epsilon by 2 power n. This is why we took 2 power n, so that series will be convergent, and this is equal to epsilon. Okay. Thus, we have M star of G minus E less than epsilon, proving 1 implies 2. Okay. Without any assumption whether E is of finite measure or not. Now we will prove 2 implies 3. 2 implies 3. From open set whose measure of the difference is less than epsilon, we have to go for a G delta set. Assume 2 holes. Then, whichever epsilon I take, I can find an open set such that, let me write, for every epsilon greater than 0, there exists G epsilon open, E is contained in G epsilon, and outer measure of the difference G epsilon minus E is less than epsilon. This I know. Now from this, I have to produce, these G epsilons are open sets. From that, I have to go for a G delta set. Please recall that G delta set is countable intersection of open sets. So I have to catch hold of countable collection of open sets. So what I will do? This is true for every epsilon. Now I have to catch hold of a countable collection of open sets. So what will I do?
Take epsilon as 1 over n.
Yes. So take, this is true for every epsilon. You work with epsilon equal to 1 by n. Therefore, for each n in n, there exists an open set. I will call it as Gn, such that E is contained in Gn. Gn is just a name, and M star of the difference Gn minus E is less than or equal to 1 by n. And this is true for all n. So you could catch hold of a countable collection of open sets. Okay. What we want is G delta set. Take the intersection. Take G to be equal to what was in the statement. I think I wrote it as V. There exists a G delta set V. So take V is equal to intersection Gn, an element of it. Then clearly V is a G delta set. Then V is a G delta set, no doubt about it. Now we have to see whether the measure requirement is satisfied. Outer measure of the difference should be equal to 0. Okay. Now, for that part, we know E is contained in Gn, right? 1 minute. Yeah. I'm a bit confused. Give me a moment. So somehow we have to prove that M star of V is M star of the difference is less than equal to 0. Equal to 0 we have to prove. Okay. So how shall I proceed? If you have some idea, you can help me. I got a V and V is G delta set. Now what I want to prove is that V should have these two properties. What are the property? E should be contained in V. That's what I am trying to get. And secondly, I should get M star of V minus E is equal to 0. So how to get that E is contained in V? What is V? V is intersection. So if E is contained in Gn, for all n, I am done. Yes, E is contained in Gn for all n. E is contained in Gn that we have. And therefore, E is contained in intersection Gn. That is, E is contained in V. So that part is over. Now I have to find M star of V minus E. Okay. Now, since E is contained in V, can I say G minus E will be contained in G? So what will be the relation? E is contained in V. So what will be the relation with G minus E, and can I say this? Gn minus E. See whether you agree with this. It is just a theory. Somehow I am getting confused from birth. Is that true? Yes or no? Why you people are not participating? I don't understand. Up to E contained in V, are you okay with it?
Yes, sir.
Yes.
Because E is contained
Yes,
in Gn, E is contained in intersection Gn, and intersection Gn I called as V. So E
Sir, what
contains
is G here?
Yes, sir. What is Z?
V.
No,
No,
sir,
sir.
G.
G.
G, sorry. Not G, what I should call V minus E. Is that okay?
Yes, sir.
V minus E. Sorry. This is V minus E. Is that okay?
Yes, sir.
Yes, sir.
How does it follow? I am not getting. So once E is contained in V, can I say V minus E will be contained in Gn minus E? How does it follow?
Because sir, V is intersection of all Gn.
V is intersection of all Gn. Okay.
So sir, V is smaller than
V
Gn.
is smaller compared to Gn, right?
Yes, sir.
Yeah. So that's also. So your confusion was I wrote a new set. Okay, I understand. So V minus E is contained in Gn minus E. Now we are done. Therefore, M star of V minus E will be less than or equal to M star of Gn minus E. Do you agree? What is that? Monotonicity. And what is M star of Gn minus E is less than or equal to 1 by N. And this is true for all N. Remember, the left hand side is now independent of N. So M star of V minus E is less than or equal to 1 by N for all N, from which you can infer that what? M star of
M star.
V minus E should be equal to 0. So thus, we could find a G delta set, and that G delta set satisfies the requirement. Like E is contained in V, and M star of the residual set V minus E is equal to 0. If you are working with an open set, the residual will have some measure, and that measure can be made less than or equal to epsilon. And if you are working with the G delta set, the residual will not have any outer measure. The outer measure is 0. Okay. So this finishes. Sorry for the small confusion I had here. Whenever this set theoretical things comes, I am a bit lazy to think and write. That's why I'm being struck. Now the third part, that is 3 implies 1, so that we can complete the cycle. 1 implies 2, 2 implies 3, and now to complete the cycle, 3 implies 1. So what 3 tells is that existence of a G delta set. Okay. Assume there exists a G delta set V such that, what was the assumption? Such that E given set is contained in V, and M star of V minus E is equal to 0. Somehow we have to prove that E is measurable. Okay. Any idea? M star of V minus E is 0. If outer measure is 0, such sets are
Measurable.
measurable. Therefore, V minus E is measurable. Since M star of V minus E is measurable, 0, V minus E is measurable. Lebesgue outer measure 0 implies that such sets are measurable. Okay. Now, do you know that V is measurable?
Yes, sir. It is a Borel set.
The G, not subset. It is a G delta set. You know, every G delta set is measurable. Every open set is measurable. In fact, Borel sigma algebra is contained in collection of all measurable sets. Okay. So G delta set is measurable. So V is measurable. Also, V is measurable, being a G delta set. So what? Now from these
We
two,
can write
E
equals V minus E.
very good. E V minus V minus. This part I will be struck if you don't say. E is equal to V minus E. V is measurable. V minus E is measurable. Therefore, E is measurable. Okay. And hence measurable because it is a sigma algebra. Therefore, we have 1. Now look at that theorem. Obviously, you can expect that that theorem has a dual. In the theorem, for every measurable set, you are producing an open set, and then you are producing a G delta set. And you know, this is sigma algebra. So once it is measurable, its complement is measurable. Okay. With all these things in hand, can you state the dual of the previous theorem? I will just state, I will not prove. Similarly, we have. Instead of working with open set, you can work with
Closed.
Closed set.
closed sets. Instead of working with G delta set, you can work with F sigma.
F sigma.
So what will be the statement of the theorem? I will not prove this theorem. Let E subset of R. The following are equivalent. 1. E is measurable. E belongs to M. Yeah, I want you to tell me the second statement. For every epsilon greater than 0, there exists a closed set. I will call F. F. Yeah. With what property?
Contained in E.
Such that F is contained in E. Inside, F is contained in E, and outer measure of the difference, E minus F, is less than epsilon. Now 3. There exists an F sigma set. Will I call F is used, V is used, W, such that W is contained in E. Inside this measurable set, you can find a F sigma set, such and the measure of the difference given set minus the subset is equal to 0. Okay, you can prove this. So these two theorems are commonly called as regularity theorems. Forget about the name. Of course, this is a straightforward theorem, it looks. However, in practice, it has a huge impact in measure theory. In fact, those theorems gives you the common strategy one follows in almost all results in measure theory, and its proof. The common strategy is the following. If you want to prove something about an arbitrary measurable set, first you prove it for a nice measurable set, maybe an open measurable set or a closed set or G delta set or an F sigma set. And once you prove this for a nice set, then use this theorem. The given measurable set can be approximated by this nice set. Okay, then try to tackle the case for the given measurable set. So that's a common strategy we follow in almost all theorems in measure theory. If you want to prove, I am telling you in very intuitive, rough manner. Once you want to prove a theorem for a general measurable set, you take a nice measurable set which approximates it, prove it for this nice measurable set, and slowly lift it to the given measurable set. And the price paid will not be too much, because you already know that given measurable set can be approximated by a nice measurable set. So in this way, though the theorems are innocent looking, it has far-reaching consequence. And I would say that that is the core of almost all theorem in measure theory. So with this, let me stop the regularity theorems there and move to the next topic. Okay. So if you recall, the purpose of introducing measure was something. What was that? Why do you want to generalize the idea of length? Why do you want to measure something other than intervals? What was the reason?
To find integration.
Find integration. That is, the Riemann integration has some shortcomings. Lebesgue wanted to remove those or rectify those shortcomings. And for that, he observed that intervals are not the good candidates to work with, but some other sets, and he wants to measure other sets. So we are going slowly to the integration theory with whatever we learned from measure theory part. Okay. So let me remind you the following before going to the next definition. That will be the fundamental definition needed for integration theory. Okay. But before going to that fundamental definition needed for integration theory, let me remind you what was the intuitive idea. Okay. So if you want to recall Raymond's theory, to a layman, Raymond's theory of integration is the following. Suppose you are given with omega equal to, let us say, closed bounded interval AB contained in R. I'm just reminding you roughly what is. So here you have AB, let us say, that is your omega, right? And you have a function f or graph of the function. So what Raymond did was he subdivided the domain AB into several subintervals, right? And in a typical subinterval, let us say ij, of course, function changes when x changes over this ij. But if the oscillation of the function is not very much, or when the oscillation is small, you can assume that the function is constant over ij. Okay. So I take a particular point xj and I calculate f at xj. And I assume that the function has same value f at xj throughout the interval ij. And I calculate f at xj times length of ij. And you do it for each subinterval, sum it, and that you are taking as integral of f, okay, approximately. And then you have to make upper sum, lower sum, etc. So this is rough idea about Raymond's integration. As I have told you in previous lectures, Lebesgue slightly modified this viewpoint. Okay? And his viewpoint was, instead of subdividing the x-axis, he subdivided the y-axis. So you have this omega here, AB. Okay. Here you have your y-axis. AB is on x-axis. And here you have a function or graph of the function. What Lebesgue did was he subdivided the y-axis into small pieces, say intervals. Okay. Now you consider a typical interval in the y-axis. Let us call it as jk. Okay. So this is jk, the interval in y-axis. Now you look for those values of x for which f of x lies in jk. Okay. I repeat, you consider those values of x for which the image f of x lies in jk. And in the diagram that I have drawn, this part is f of x that is lying in jk. So those values of x would be this. Okay, this part. For this part of the domain, f of x lies in jk. Similarly, I think here also. Okay, and also here. So all these three parts of x-axis, or more specifically inside interval AB, if you calculate your f of x will lie in JK. Am I right? I don't know whether the diagram that I have drawn is convincing for you, but the idea should be clear. Take y-axis, divide into several subintervals. I took a typical subinterval JK, and I am looking at those values of x for which my f of x lies in interval JK. Do you agree with what I have drawn?
Yes, sir.
Yes, sir.
So these three parts of the domain has x values whose fx is in JK. Now it is natural to do the following. What Rayman did was, in the subinterval ij, he took a representative value f of xj and assumed that the function is constant throughout that interval. What Lebesgue essentially does is the following. In this jk, which is the representative subinterval in y-axis, you consider a particular value, one specific value, one representative, that is yk. Okay, so yk is some specific representative value in jk. Now you multiply this with those x in the domain for which f of x is in jk. That is these three subintervals, these three parts. All of them together I will call AK. So what is AK? AK is the part in the domain whose image is in JK. Okay. In other words, it is F inverse of JK, right? F inverse of JK you find. And then you take its measure, multiply it with the representative value, do it for each subinterval in the y-axis and sum it. And that can be taken as an approximate of integral. This was Lebesgue idea. So subdivide y-axis, in each typical subinterval, take a representative, that is yk. Now, consider the interval containing yk and consider those x values for which fx lies in that interval, jk in our notation, and find its measure. Okay. Because this f inverse of jk may not be an interval. In the diagram that I have written or I have drawn, this f inverse jk comprises of three intervals. But in general, it may not be an interval at all. Okay. Is that clear roughly? This is the idea of Lebesgue. Is that clear?
Yes, sir.
Yes, sir.
Now, if this definition to be valid, look at the right hand side. I am not telling a rigorous treatment here, okay? I am just giving you what is the basic intuitive idea. Look at the right hand side. It involves measure of f inverse of jk. So for this definition to be meaningful, what should be defined first of all? Look at the right hand side. If you want to talk about the measure, that set should be first of all measurable.
Measurable.
Measurable. So you want f inverse jk to be
Measurable.
What is jk? Interval. Jk is an interval. So you want those functions for which inverse of intervals are
Measurable.
measurable. So it naturally tempts us to make a definition. Those functions such that whose inverse image and inverse image of intervals are measurable will be called as measurable functions. And this is the primitive idea to go for integration theory. So I am going to define what is measurable function. Okay. Before that, let me just quickly write what can be a rough definition. Thus, for the above expression to be meaningful, we need F inverse of JK to be measurable. Forget about Lebesgue measure, okay? Any measure you can work with, but this F inverse JK should be measurable. For our case, it will be Lebesgue measure. Thus, therefore, naturally, we should consider those functions whose inverse image of intervals are measurable. And this is what we do in measurable functions. Not exactly, but this is the idea. Finally, we want inverse image of intervals to be measurable. Okay. With this understanding, now let me make a precise definition. Now, though we have used it several times, I have not recorded it properly. I have not written it anywhere. It is always convenient to work with extended real number system in measure theory. For instance, even when you define outer measure M star, you are using L of In. That In's can be of infinite length. Then L of In may be infinity. Okay. So we have to deal with cases where you have values to be infinity. So instead of working with the reals, you have to work with extended reals. Okay. So let me just note down a few things about extended real number system. So far, I have not written it down neatly. So it is always convenient to work with, in the measure theory I am talking, extended real number system. To extend real numbers, what do you mean by extended real number system? Means along with the real number, you add two simples. It is convenient to extend real numbers by what should I say, joining or adjoining, by inserting two simples, infinity and minus infinity, and R bar, I would say R union infinity minus infinity. Okay. What I want to note down is, what are all the order properties that you introduce? In R, you know already there is an order, less than or equal to. Okay. So here, along with the real number, how this infinity and minus infinity interact in the order. We consider the following. The following are like axioms. Minus infinity is less than A is less than plus infinity for all A in R. So these two symbols that you have introduced will interact with elements in R in this way. Okay. Further, that is one thing. Now, how these symbols interacts with the algebraic operation, plus and so on. A plus infinity, I will take as infinity for every A in R, and also for infinity. That means infinity plus infinity, I will take as infinity. Now, A into infinity, I will take as infinity if A is greater than 0 and minus infinity if A is less than 0. Okay. Infinity into infinity convention is we will take it as infinity. Okay. Now, similarly, you can have for a minus infinity. But one thing that is very special to measure theory is 0 into infinity, we will take as 0, not indeterminate. 0 into infinity, we will take as 0 because it is going to be consistent with the infinite measure of a function or a set that we are going to deal with. It will not contradict any of the things. It will be consistent with our results that we prove about measures and so on. So this is a convenient convention we use exclusively in measure theory. 0 into infinity is 0. Okay. Similarly for minus infinity. So I should write somewhere this, otherwise. So I thought this is the correct point where I can write about extended real number system. Okay, you may be knowing it. Only one thing that you should keep in mind in addition is 0 into infinity is taken as infinity. Sorry, 0. 0 into infinity is taken as 0. And further, one thing that you should keep in mind that infinity minus infinity is left undefined. We will not try to make any convention regarding infinity minus infinity because you cannot make any convention which is consistent with what we already have about the other real number system, etc. So that's why this we don't want it to touch. That will be left undefined. Okay. Now, as I told, our intention is to deal with measurable function. Again, in most of the cases, it is convenient to work with the extended functions, not real valued function, extended real valued function. That means functions can take values in this R bar. Codomain is R bar. Okay. So now let me make precise definition of measurable function. In our setting, that is Lebesgue measure and things like that, Lebesgue outer measure and Lebesgue measure, the definition of measurable function is taken as follows. In more abstract setting, I will define later. Let f be an extended real valued function whose domain is measurable. Whose domain is a measurable set. When I say measurable, I mean Lebesgue measurable. Here, we say that f is measurable. When will you say a function is measurable? F is measurable. Intuitive understanding is that you want the inverse image of intervals to be measurable. We say that f is measurable if for each real number, each alpha in R, the set of all x were in the domain such that f of x is greater than alpha, which will be same as f inverse of alpha infinity is measurable. I'm not considering interval of arbitrary form. I'm considering only intervals, inverse image of the intervals of the form alpha comma infinity. It is enough to consider this. You will see soon. Okay. So this is the definition of measurability. If you want to call a function to be measurable, first of all, its domain should be a measurable set. And secondly, inverse image of every open interval of the form alpha comma infinity should be measurable. Or the set of all x in the domain for which fx is greater than a particular level alpha should be measurable, and this should be true for all alpha in R. It should be true for all alpha in R. So, hope you understood the definition, but the back of your mind, you should understand that our aim is to have inverse image of intervals to be measurable, so that we can slowly go to the Lebesgue integration theorem. Now we have the following theorem. There is nothing special about the interval of this form. That's what the theorem essentially says. The following are equivalent. Following are equivalent. So this theorem will tell you that there are many ways to consider measurable functions. One way is to see that for each alpha real number, f inverse of open interval alpha infinity is measurable, but if that is equivalent to say in different forms. What is that? So let me write all the statements one by one. The following are equivalent. 1. F is measurable. Let me write here, f is a function from E to R bar, where E is measurable. E is a subset of R, measurable. Codomain can be extended real. F is measurable, definition I have made, but that definition is equivalent to saying that for every alpha in R, set of all x in the domain, such that f of x, in the definition I used greater than alpha, greater than or equal to alpha is measurable. Is measurable. Then 3. For each alpha in R, the set of all x such that f of x less than alpha is measurable. So you can define like this also, measurable functions. And 4th, for each real number alpha, set of all x, f of x less than or equal to alpha is measurable. All these 4 are equivalent. So essentially, you can view measurability of a function in many ways. Either you can say f inverse of open interval alpha infinity should be measurable for each alpha, or you can say f inverse of closed alpha open infinity should be measurable for each alpha, and so on. Okay. Without further ado, let us go for the proof, which is simple set theory. First, let me prove 1 implies 2. 1 is the definition, measurability that we took. What was that? Set of all x such that f of x greater than alpha is measurable. With the help of that, I have to prove f of x greater than or equal to alpha is measurable. Okay. Suppose f is measurable. This is my assumption. That means inverse image of alpha comma infinity is measurable for open alpha infinity. Now let alpha is in R. What I have to prove? Set of all x such that f of x greater than or equal to alpha. This I have to prove that it is measurable for any alpha. Alpha I have already taken to be arbitrary. Okay. So how do you do that? I know that f is measurable. That means I know that collection of all x such that f of x greater than, let us say, beta is measurable for all beta. So can you write f of x greater than or equal to alpha in terms of f of x greater than something?
Alpha plus epsilon.
Okay. But epsilon, it's difficult to deal with because it is uncountable. So I will take countable 1 by n type. Okay. So I will write this as intersection set of all x such that f of x strictly greater than alpha minus 1 by n. N over n. I want f of x to be greater than or equal to alpha. I am taking alpha minus 1 by n for each n. And then fx greater than alpha minus 1 by n for each 1 by n. Okay. Will you agree with this equation? Is it easy to prove? Yes or no? It is intersection, not union. Intersection. Can you prove this? Yes or no?
Yes.
Why this much delay? Fx greater than or equal to alpha. Take one part first. Suppose your x is such that f of x is greater than or equal to alpha. Can you say that f of x will be greater than alpha minus 1 by n?
Yes, sir.
So that part is over. So this for each n, and therefore it will be in the intersection. So left hand side contained in right hand side set is clear. Now similarly you go for the other. Suppose your x is such that f of x is greater than alpha minus 1 by n for all n. Then definitely f of x should be greater than or equal to alpha. And that will give you that the set in the right hand side is contained in set in the left hand side. So this is obvious. Now, by the assumption that f is measurable, do you see that the right hand side is measurable?
Yes, sir.
Yes, sir.
Because it is intersection of measurable sets, okay, which is measurable. Not arbitrary intersection, it is countable intersection, which is measurable. Therefore, 1 implies 2. Now, 2 implies 3. What was 3? 3 was, I think, fx less than alpha. Fx less than alpha. Yes. So, suppose for each alpha in R, set of all x such that fx less than, sorry, what was our assumption? 2 greater than or equal to alpha is measurable. Greater than or equal to alpha is measurable. Okay. This is our assumption to prove that less than alpha is measurable. Let alpha is in R. Somehow, I have to prove that set of all x such that f of x less than alpha is measurable. I think that is straightforward. Do you see that this is measurable?
Yes,
Yes,
sir.
sir.
Why?
Complement.
Complement. It's complement. Set of all x such that f of x greater than or equal to alpha complement. Therefore, and hence measurable. It is just set theory and hence measurable. So 2 implies 3 is over. Now 3 implies 4. 3 implies 4. What was 3? Less than alpha. Okay. Now we want to deal with less than or equal to alpha. Similar to what we did. 1 implies 2. Same thing. Let alpha element of R. I have to deal with set of all x such that f of x less than or equal to alpha. Using 3. What was 3? Less than alpha. So how do I do? This is collection of all x. You make fx to be less than alpha plus 1 by n. And it should be true for each n, intersection n, which is measurable. So that gives you 3 implies 4. Now 4 implies 1 to complete the cycle. What is 4? Fx less than or equal to alpha is measurable. And what you have to prove? F is measurable. Less than alpha you have to. Less than alpha? No. Greater than alpha you have to. For each alpha in R, I want to see whether set of all x such that f of x greater than alpha. That is our definition. Using less than or equal to alpha. Straightforward again, complement. F of x less than or equal to alpha, complement, and hence measurable. And hence measurable. So we have defined measurability as collection of all x for which fx greater than alpha should be measurable for each alpha, but that can be viewed in variety of different ways. That's what the theorem says. So different authors may define in different way. But before proceeding with it, let me ask one question, namely the following. When I started to define measurable function, I told that everything is motivated by Lebesgue integration. And for Lebesgue integration, what we need is inverse image of intervals are measurable. But we have not defined in that manner. But do you see that if f is measurable, then inverse image of intervals will be measurable? If the question makes sense, suppose we take our definition of measurability. With that, can you prove that inverse image of intervals will be measurable? Yes or no? F inverse of, let us say, closed interval AB. Can you write in terms of some of these sets?
Yes, sir.
F inverse of closed bounded interval AB. Can you write it in some of the way in these 4 listed? 4 ways in which I have listed the. Yes or no?
Yes, sir.
Therefore,
Yes.
our definition of measurability will automatically imply that inverse image of intervals will be
Interval.
Measurable.
measurable. Inverse image of intervals will be measurable. Yo, please don't say interval. Okay, I don't say that the inverse image of intervals will be interval. It will be measurable. F inverse of AB, if you find, it will be again a measurable set. Okay. Measurable sets can be very much complicated. It cannot be an. It may not be an interval. Anyway. Okay. Now let me quickly give some examples. So our progress so far is just we have defined the measurability concept of a function. Let me take constant function. Let E be a measurable set. Maybe R itself you can take measurable subset of R. Measurable set in R. Maybe R itself you can take. And I define F from E to R. Okay. As f of x is equal to some constant for every x in E. Constant functions. Question is whether this will be measurable. Check applying the definition. Okay. For applying the definition, what I should do? I should start with an arbitrary alpha. Let alpha in R. And I should consider collection of all x such that fx is greater than alpha. And I want to see that this is measurable. Now, what will be collection of all x such that fx is greater than alpha? Fx can take only 2 values. Sorry, fx can take only 1 value, which is c. So what will be the collection of all x such that fx is greater than alpha?
So if alpha is greater than c, then it will be phi.
It will be null set if alpha is greater than c, because you don't have any x for which fx is greater than c. Fx is in fact equal to c. And if alpha is less than c, what will happen?
Open alpha,
Alpha
comma
comma
c.
infinity.
No, what will be that set? If alpha is less than c,
E.
Is
full domain E, right? And what about if alpha is equal to C? Set of all x such that fx is greater than C. Fx is only C, right? So again,
phi.
5.
Phi.
Now, whether all these sets are measurable, null set and E are the possibility. So possibility of this set is either null set or E. Null set is measurable and E is measurable. Yes or no? You
Yes.
started with a measurable domain. Therefore, collection of all x such that fx greater than alpha, give me 5 minutes, is measurable. And that gives you that f is measurable. E can be taken as R itself, okay? F is measurable. So constant functions are measurable. Constant functions are measurable, okay? Now let me give you another example. Let A be a subset of R, and I define chi A from R to R. How do I define? Characteristic function. I hope you know indicator function. Chi Ax is 1 if x is in A, and it is 0 if x is not in A. This is my definition. Okay. It is not defined on entire R. R is measurable. So the domain is measurable, and I am taking chi A from R to R like this. Now my question is whether this will be measurable or not. Chi A is measurable or not. Okay. So let us see. Let me consider A to be a measurable set. Let A be a measurable set. Measurable subset of R. Okay. We prove that chi A is a measurable function. Measurable function. And for that, what I have to do? Let alpha in R. I am going to apply the definition. Collection of all x such that fx greater than alpha I have to consider. Now tell me what it will be. Remember, fx can take only two values, 1 and 0. F here is chi ax. Okay. You have to find chi ax. Yeah. Can you tell me what will be this? Chi ax can take only two values, 1 or 0. You have to split into several cases. Alpha is real number. Suppose alpha is less than 0. Alpha is less than 0. Then are you there? If alpha is less than 0, what are all the possible x for which chi ax is greater than alpha?
R.
A, sir.
Entire A, right? Because chi ax can take only value 1 and 0. Both 1 and 0 are greater than alpha if alpha is negative, right? So it will be entire R. Entire R. Do you agree?
Yes, sir.
Now if alpha is equal to 0, if alpha is equal to 0, you want chi ax to be greater than 0. When chi ax greater than 0 means chi ax can take only value 1. And where it takes value 1?
A.
A.
A. So this will be A. This will be A. And third possibility is alpha is greater than 0. Okay. But again, alpha greater than 0, you cannot consider at a stretch, I think, because if you want chi-ax to be greater than alpha, but chi-ax can take only two values, either 1 or 0. Okay, so what should I consider here? Alpha. Suppose alpha is greater than 1.
R minus
Suppose alpha is greater than 1. Then chi-ax greater than 1. Will it happen?
no sir.
No. So this is again
Empty.
null set. Now I don't know whether this much cases I have to consider. You can write it more briefly maybe. Now I will consider 0 less than alpha less than 1. Alpha is some number between 0 and 1. Then I want chi-ax to be greater than that. That means only possibility is 1, right?
R minus A.
So what is that? Only possibility is
A complement.
R
A.
minus A.
A complement or A. Suppose I want
A.
chi-ax to be greater than half. A, again A. So somewhere it should come a complement also, I hope. Where it will come. Now what about if I take alpha equal to 1? Chi-ax greater than 1. Chi-ax greater than 1 can never happen, right? So that will be again, so here it will be, so some cases we are missing. I don't know where it is. Let us check again. When alpha is 0, what happens? Alpha is 0. I want chi-ax to be greater than 0. Chi-ax greater than 0 means only possibility is chi-ax is 1. Okay. So that means A complement will never come or what? Anyway, so you consider all these cases and you can see that all these sets are measurable. Yes or no? R is measurable, null set is measurable, and A is assumed to be measurable. Therefore, you check this, okay? This equation you have to check. I don't want to spend time on this. Check it.
Okay sir.
And you can see that all these things are measurable. Yes or no?
Yes, sir.
Yes sir.
R, A, null set A. Sometimes A complement may also come. I don't know. You have to check it. So, but if A is measurable, A complement will be measurable. Okay. So, in any case, this possibility of all these possibility can be exhausted, and all these things will be measurable. So, which are measurable. So that means for any alpha, you get x chi-ax greater than alpha to be measurable. Therefore, chi-a is measurable. Therefore, chi-a is measurable. So characteristic function is measurable if the set A is measurable. And I will give an exercise. The converse is true. With that, I will stop. That is, chi-a is measurable implies A is measurable. It is again easy to see from this. Suppose your chi-a is measurable, then all these sets should be measurable, right?
Yes.
Yes, sir.
Because you want for
Yes.
each alpha this set to be measurable. So all these things should be measurable. That means A should be measurable. Okay. So it's function or characteristic function is measurable if and only if the set on which the indicator function is defined. This is called indicator function on A. Domain is R, but this is called indicator function on A. That A should be measurable. Then it will be a measurable function. So I have given you plenty of examples of measurable function. Can you give me one example of a non-measurable function?
P.
P.
So
The hint is use the previous example that I have given. Characteristic function is measurable only when you take A to be
Measurable.
Measurable.
So you take A to be a
Non-measurable set.
Non-measurable.
non-measurable
Measurable.
set and define characteristic function on that A. Do you have a non-measurable set?
Yes, sir.
Yes,
sir.
you have proved. You have proved. So once you know non-measurable set exists, then using this example, you can construct non-measurable functions. Okay, characteristic function on a non-measurable set will be non-measurable. Okay, so with this I will stop, and the syllabus for the examination is till measurable function, which is introduced today. I cannot ask much because I have only defined and gave some examples. Yeah. And exam will be as per